Why am I doing a new video on the topic of supply and demand? Well, it's become clear to me from comments people are putting on the previous videos that my account of why demand theory has more free variables than unknowns was a bit too cryptic and technical. So I'm going to try and explain this in more detail. So the first thing is to say, what was the attitude of Marx to supply and demand? He says that supply and demand regulate nothing but the temporary fluctuations of market prices. They'll explain to you why the market prices of a commodity rises above or sinks below its value, but they never account for the value itself. At the moment when supply and demand equilibrate each other and cease to act, the market price of a commodity coincides with its real value, with the standard price around which its market prices oscillate. In inquiring into the nature of value, we have therefore nothing at all to do with the temporary effects of market prices of supply and demand. Now, in saying that, Marx was sticking to the line of his predecessors. So Ricardo had said, it is the cost of production which must ultimately regulate the price of commodities, and not, as has often been said, the proportion between supply and demand. The proportion between supply and demand may indeed, for a time, affect the market value of a commodity, until it is supplied in greater or less abundance, according as the demand may have increased or diminished, but the effect will only be of temporary duration. And Adam Smith before that said, when the quantity of any commodity which is brought to market falls short of the effectual demand, all those who are willing to pay the whole value of the rent, wages and profit, which must be paid in order to bring it thither, cannot be supplied with the quantity they want. Rather than want it altogether, some of them will be willing to give more. He's using the word want in a slightly archaic 18th century use there. Now, you have to realise that in Smith, the term natural price corresponds to what Ricardo and Marx called value. And Smith held that supply and demand could only bring temporary fluctuations around the natural price. All the classicals, to a greater or lesser extent of clarity, agree that the labour required for production is the source of value. Supply and demand only produce temporary fluctuations, and this had political consequences. If you accept that labour is the source of value, the Ricardian socialists could argue that labour had the right to the full value of product. Now, this was obviously an ideological problem for capitalist economics, and it was resolved by Marshall, who aimed to overcome the disequilibrium view of the classicals, in which market price was given with one in which the market price was given by the intersection of supply and demand curves. Previously, the classical economists had said the equilibrium price is the labour value, and supply and demand are disequilibrium phenomena. Instead, Marshall says no, supply and demand interact to produce an equilibrium, which is the market price. And this has been the standard treatment by neoclassical economists ever since. And the diagram to the right is Marshall's original supply and demand curve, hand-drawn in his book Economics. This had certain ideological advantages. If supply and demand explain equilibrium price, then you can dispense with the classical theory that supply and demand were just disturbing factors. And if supply and demand determine value, then the labour theory of value can be discarded. It was no longer necessary to explain the centre of gravity of prices, because that was now given by the intersection of these two curves. Now, I'm going to examine the curves Marshall gave in some detail. Now, at one level, these curves are just something he sketched on graph paper with actual values for them. And I'm going to examine them in detail because once you examine them algebraically, you see what nonsense this whole theory is. Let's look at his demand curve. This curve here, the buyer's demand curve. Now, because it's turning down, sloping down but curved, because it's not a straight line, it must be at least a second order polynomial. So the function d of q, where q is the quantity, can be expressed as a polynomial, a constant a plus a constant b times q plus a constant c times q squared. You need at least a second order polynomial to do that. Since Marshall gives actual points, we can solve this polynomial. He shows that when demand is zero and price is 15. So we know A must be 15 in his equation. When demand is 10, price is 9. When demand is 13, price is 8. So we can fill these in and get two other points of his polynomial. Now with two unknowns, two other points, we can solve the polynomial. First we simplify it into 10b plus 100c equals minus 6, 13b plus 169c equals minus 7. If we eliminate b by multiplying the top row by 1.3 and subtracting it from the bottom row, we get the equation 39. There's a standard Gaussian elimination. We get the equation 39c equals 0.8. So c equals 0.205. And filling this into the equation 10b plus 100c equals minus 6, we can solve that b must be 0.85. So we actually can deduce from the curve he's drawn what the equation for demand is. The demand, as expressed as a quantity, is 15 minus 0.85 q plus 0.205 q squared. That's actually the equation for the curve he's drawn. And let's look at this. It's a really odd formula. And it's got three constants: 15, 0.805, 0.205. And where does he get these constants from? Well, he just made them up. He plays, let's suppose that this is the function. But he doesn't write it down explicitly as a polynomial, because once you write it down explicitly as a polynomial, it's clear that it's totally arbitrary, senseless equation. But behind the scenes, that's the equation he's got. Now, if we look at his supply curve, it's even more complicated. We see it curves one way, then it curves the other way. So it must be at least a third degree polynomial. So it must be an equation of this form. Up arrow means squared and cubed. Sorry, I should have formulated it properly. I'm not going to derive the actual graph, actual values for the constants E, F, G and H from his graph. That's just tedious to go through the steps. But the full set of equations that Marshall has for the determination of price is a demand function, A plus BQ plus CQ squared, and a supply function, SQ equals E plus FQ plus GQ squared plus HQ to the power of 3. And he then says the equilibrium is given by DQ equals SQ. And he claims that his maths enables him to simultaneously obtain in the price that will obtain and the quantity that will be sold. Well, just as a piece of deduction, that's fair enough. But note that he's got 7 free variables: A, B, C, E, F, G and H. Now, where do these come from? As I said, he just makes them up. But in general, if you want to formulate a mathematical rule explaining a phenomena, a rule that you want to say is a law that governs that phenomena, according to the mathematician and philosopher Leibniz. It should have as few free variables as possible. Now, we can illustrate that with Leibniz's contemporary Newton, who formulates his law of universal gravitation. His law of universal gravitation says that force is a function of the mass of planet 1, the mass of body 2, and the distance between them. And it takes the form g m1 m2 d squared. Sorry, over d squared. I've missed out a term. Put that back in. Three explicit parameters: the masses of the two bodies and their distance. In addition to that, one free variable, the universal gravitational constant, g. Now that's a free variable, and that has to be filled in. It has to be given a value before you can use Newton's equations to work out the force between the Earth and the Moon, or the force between the Sun and the Earth. You need to know the masses, the distances, and you need to know g. So how do you determine what g is? Well, it can be done experimentally. Cavendish in 1897 used a technique called a torsion balance to measure what the gravitational force is. And the torsion balance involved two large lead weights here and two iron weights here and a thin wire which could take rotation and act as a slight spring, and by adjusting the distance between the bar and the balls, moving the balls together, he could measure the force by the degree of deflection of the lower bar. And he measured the degree of deflection by a mirror which he shone a beam through and saw by how much the beam was deflected to give a measurement of the force acting there. So in principle, the g could be measured experimentally. Now let's take another theory from the 18th century. The Smith-Ricardo labour theory of value says that the price of commodity X is given by the labour content of X divided by the labour content of a pound of silver. That's the price in terms of silver. It has only two variables, both of which are in principle measurable, and it's got zero free variables. Smith actually examines the price of corn in terms of silver and the influence of more productive silver mines coming in into production to see that. Now, he has a testable theory here, Smith has, because were it the case that the productivity of agriculture were rising, that is to say, more bushels of corn were produced per labour, and the productivity of silver were falling, and that is to say, the silver mines were getting depleted and requiring more labour, Smith's prediction is that the formula predicts that silver price of corn will fall. That is to say, a given pound of silver will buy more corn. If we found historically that in fact the silver price of corn rose, then Smith's theory of price would have been falsified. Smith actually went back looking at price records of corn on the Winchester market to 1200 AD. He's writing in the mid 1700s. So he looked 500 years back at the corn prices to test his theory. Now, let's go back to Marshall. Marshall's got his 7 free variables, but he has no practical way of measuring any of these constants. They're just virtual constants that he's imagined. What can you observe in practice? All you can observe is that at the Winchester market, so many tons of corn were sold, and that it was sold for, say, 3 shillings and 6pence a bushel. This allows you to fix at most 2 of 7 free variables. If you've got 2 observables, an equation with 7 variables, you've only got 2 constraints, and that leaves, sorry, that should say leave 5 as a fudge factor. Now, could you get over this with a time series? Could you take a time series of prices and quantities, which Smith did with corn prices? No, you can't. Because according to Marshall's theory, any change in price involves a change in either the supply or demand function. Let's assume only demand is changing. At time 1, we have demand function 1, which has got constants A1, B1 and C1. At time 2, we have demand function 2 with A2, B2 and C2. Now, we now have observations in the year, let's say, 1200 and the year 1300. We have 10 free variables instead of the original 7. The original 7 plus the 3 new ones for the year 1300. So we've got 4 observations, 2 prices and 2 quantities. But whereas previously we had 5 extra free variables, now we've got 6 extra free variables. The longer the time series you use, the more underdetermined becomes Marshall's theory. Now, mathematically you say a set of equations are underdetermined when there aren't enough equations to constrain the free variables. And another way of saying that is that if you've got an underdetermined theory, it's essentially random. An underdetermined theory is compatible with any observation. You can play around with the free variables to make it fit anything, and has no scientific predictive power. This is the point that Leibniz makes, that you can put down any random series of dots and fit a function through it, but unless your function contains a lot less free variables than observations, it can't be treated as a law. So how did Marshall pull off this confidence trick? This mathematical absurdity? How did he get it accepted? Well, I think it's through the trick of using visual reasoning rather than algebraic reasoning. It's partly what I call the power of icons. This was, I can't remember which classical philosopher observed that if you stare daily at the statue of Diana or of any of the gods, you come to believe that the God really exists. And Catholics who go in and adore the icon of the Virgin Mary come to believe that the Blessed Virgin is real because they look at this icon so often. It forms a concept in their mind that there really is a thing corresponding to the icon. If you show students an icon, in this case the icon of these supply and demand curves, and they look at it repeatedly through their studies, they will come to believe that these curves represent something real, rather than just something that Marshall scribbled on a sheet of graph paper. Pictures are powerful because they enter the brain via the visual cortex in an immediate and uncritical way. Sometimes this is useful in maths. This is why Venn diagrams are easier to work with when teaching set theory than using formal set theory. It's much easier to understand because it enters directly into the highly parallel part of our brain, the visual cortex, which is the most powerful information processing section of our brain. But it is an intuitive information processing system. It's not a deductive and critical system. If you want to go into this in more detail, I can advise you to read Lakov and Nunes's book on the underlying neural basis of maths. It's called Where Mathematics Comes From. Now, Marshall's supply curves have an intuitive appeal, but as soon as we translated them into algebra, we saw there were problems. The point is, don't trust optical illusions. Your brain, your visual cortex, is very susceptible to optical illusions. Instead of relying on visual images like that, which are okay for pedagogy, but if you want to see whether something's true, don't trust optical illusions. Actually, look